Now let's see what is a repeat loop. This repeat loop is not available in C language, it is available in Verilog. What does it do? It will repeat for certain amount of times. If you want to repeat it for 5 times, just repeat 5. If you want to repeat it for 50 times, just write 50 times. So the repeat loop execute for fixed number of times. That is the purpose of repeat loop. You have some set of statements and you want to repeat the set of statements for particular number of times. Okay. The important thing you need to remember is it cannot be used to loop on a general logic expression. Till now in while and for loop, what we have seen, they will be looped based on the logic expression or condition, whether if it is less than 128 or if it is greater than 5, any condition, right? But in the repeat case, it should not be like that. You have to particularly define how many number of times you want to repeat. You should not give any condition here. Let's say repeat less than 50. This is not valid. You have to give particular number of times, then only the repeat loop will work. The repeat number, which is a constant variable or signal value, cannot be evaluated while loop. What I meant is you have to write the number whatever before you are entering into the looping statement. Right? You can give directly number or you can give variable like number of cycles. You can give NOC you can give, and this NOC should be defined prior, like a parameter. You can take parameter and then define your NOC is equals to, let's say, 10. But this NOC, repeat NOC, so what does it mean? It will repeat the set of statements for 10 times. But you cannot assign NOC inside the looping statement. You cannot change my NOC now to 50. It won't happen because you are already fixing it to repeat for 10 times. You cannot change the NOC to 50 and you will expect 50 times it will repeat. So this thing you should avoid. The looping number cannot be evaluated while looping, right? The repeat number cannot be evaluated while looping. So let's take the same example of count up to 128. So how to write that? Using repeat statement. You again start with initial, begin. Here you'll start with count is equals to 0. Okay. Now you write repeat. Repeat how many times? 128 times. Repeat 128 times. What do you want to repeat? If it is multiple line of statements, you should write in begin and end. Begin, display, same statement I'm displaying. Count is equals to percentage d, comma count. Since I want to increment the count, I have to write count is equals to count plus 1. See, I am incrementing the count, but not the repeat number. Repeat number is already fixed to 128. I can increment the count or whatever statement I want, but I should not increment or change this value. Okay, and then end. So this is how you can repeat the same task that you have performed using while and for loop. You can do the same thing using repeat loop also. And instead of just giving a number, you can give a variable also. As I told, you can give, let's say, cycles. Cycles is your variable. Then you define the parameter dot cycles, parameter, not dot, directly parameter cycles is equals to 128. Before entering into the initial block, you define this and then initial, begin, then you will write same line of codes. Here you will write, instead of repeat 128, you can write repeat number of cycles you want, right? Repeat, instead of 128, you can write the variable name cycles. And then you will write these statements, begin, count is display the count, and count is equals to count plus 1. But you should not do any operations on cycles variable, because that will define the number of times that repeat loop should be repeated. So you should not use repeat cycle inside the repeat block, inside the begin end of the repeat block. Okay, you can not just display, you can use like events also inside the repeat block. If you want to repeat 128 times and then 128 times of number of times of the cycles, let's say repeat for cycle times. Here my cycle can be anything, 128 or 1280, any number of cycles. Here you can even write event based statements also like this. Let's say begin at the rate of pausage clock. You do some buffer is equals to 1 tick binary 0, any statement. So what I meant to say is the repeat block can also have event controlled statements also, not just displaying something or not just incrementing something. You can have event controlled also. Whenever there is a positive edge of clock, then this statement will be executed and this entire block will be repeated for number of cycles that you have defined here in parameter. Okay. So this is how you can use the repeat loop in Verilog. And finally, there is one more looping statement called forever loop. The name itself is suggesting it will repeat for forever. It will repeat for n number of times, infinite number of times. So the loop does not contain any expression and execute forever until the finish. Dollar finish is a system task. Until the dollar finish is encountered, it will repeat for forever. So what is its main purpose? One of the example is to generate the clock. Earlier, how we used to generate the clock? We used to initial clock is equals to 1 tick binary 0, and then we used an always block. Always after 5 nanoseconds, let's say my clock is equals to negation of clock. Right? We used clock generation like this. So what does it do? Initially at 0, clock is equals to 0. After 5 nanoseconds of time period, clock will be changed from 0 to 1. Again after 5 nanoseconds, it will change from 1 to 0. Right? The same thing you can define by using forever block also with just initial statement. You don't need to write an always statement also. So how to do the same clock using forever? You write initial, then your clock is equals to 1 tick binary 0. Now you use the forever keyword to define the forever loop. So how to write forever? So multiple lines of statements. So I have to write begin and then begin forever after every 5 nanoseconds or 5 time units. My clock is equals to negation of clock. That's it. The same this line of code will also result into same kind of clock. Okay. You can do the event based as we did in the repeat also. You can do here also forever at the rate of pausage of clock. You can do event based statements also at the rate of pausage clock. Assign my q is equals to d, something like this. Okay. This is the use of forever loop. So while we do the live coding, I want to show something why this hashtag 5 is not a synthesizable delay. We have already seen that is not a synthesizable delay. In case of data flow modeling, if you remember, we have did a end operation using this delay operator, and we try to create a 2 seconds of delay, but it won't happen because it is not synthesizable. But in this live example, I want to show why it is not synthesizable. I mean, what do I mean by not synthesizable? Not synthesizable means it won't create any output. We'll see in the live coding session. Okay. So that is all about the different looping statements that are available in Verilog. Now we will move to one more topic called sequential and parallel blocks. Till now we are using begin and end, right? I already told the begin and end are sequential block, and there are some other keywords like fork and join which can define parallel block. We'll see what is the sequential blocks and what are the parallel blocks, and there is a special feature that is available in which you can nested use different sequential and parallel blocks in a single code, single module. Okay, you can even nest both sequential block as well as parallel blocks. Okay, so first of all, we will see what is a sequential block. The statements in sequential block execute in the order. Okay, that is what sequential means. Whatever the statements you have written inside the begin and end, they will execute sequentially. First statement will execute first and last statement will execute last. But there is an exception. We have already seen this while we are doing live coding, right? We have defined 4 different cases. Blocking statement with regular delay, blocking statement with inter-assignment delay, non-blocking statement with regular delay, non-blocking statement with inter-assignment delay. Except non-blocking statement with inter-assignment delay, the sequential block will execute in order. We have seen this in the live coding session, right? What happened there? If you have non-blocking statement, non-blocking assignment with intra-assignment delay, not regular delay, intra-assignment delay, right? This is regular delay and this is intra-assignment delay. In that case, it will schedule, not wait for that particular amount of time period. It will schedule that and it will execute. So in that case, it won't follow the order. It will follow the precedence of non-blocking assignments. We have already seen this in the previous session. So this is the only exception in sequential block. Otherwise, all the statements will be executed in order that you have defined. So let's see two examples: sequential block without delay and with delay. So I am defining two different examples using sequential block without delay and with delay. So let's take this is without delay. We'll see what happens, and with delay, we'll see what happens. Okay, I'm in the initial block, I'm using begin and end. If I'm using begin and end means this is a sequential block. Inside the sequential block, I'm assigning my x is equals to 1 tick binary 0, my y is equals to 1 tick binary 1, my z is equals to concatenation of x comma y. Okay, let's say my t is equals to concatenation of y comma x. Okay, these are the four statements I'm using, and I'm not using any delays, right? So what happens? Ideally, all these statements will execute at simulation time period of t is equals to 0 because it is inside the initial block. All the initial blocks will be executed at time period of 0, right? At time of 0. So they will all execute at time 0, but they will follow this order. Okay. So first x is equals to 0 will be executed, then y is equals to 1 will be executed, then my z will be 0 1, my t will be 1 0. Okay. Because they are inside the begin and end block, they will execute in a order that you have specified. So let's see what happens if you give some delay for the same set of statements. I'm giving a delay. Let's say my x is equals to 1 tick binary 0 at time t is equals to 0, and after 5 nanoseconds my y is equals to 1 tick binary 1, and after 10 nanoseconds my z is equals to concatenation of x comma y. You should not use parenthesis if you are using concatenation, right? You can directly write x comma y. Similarly here also x y and y x. And after let's say 20 nanoseconds, my t is equals to y comma x. So we'll see at what time period these will be executed. At time period t, this will be executed, right? Because initial block will start at time 0. So at time 0, x is equal to 0 will be executed, and at time t is equals to 5, because we have given 5 nanoseconds of regular delay, not intra-assignment delay, and this is a blocking statement as well. Since it is a blocking statement, it will block for 5 nanoseconds time period, and then after 5 nanoseconds time period, it will release the control flow and it will go to this statement. So this will be executed at 5 plus 10 nanoseconds. So at 15 nanoseconds, the Z will be 0 1, and this will be executed at 5 plus 10 plus 20. How much it is? 35. At 35 nanoseconds, my t will be 1 0. Okay. Since they are blocking statements, they are blocking the flow, so they have to add the earlier time periods. Okay, this is with delay and this is without delay, but we have already seen these things from past few sessions since we are using only begin and end. Now let's see the new concept, parallel blocks. So the statements inside the parallel blocks executes concurrently. Concurrently means all at the same time. So you can use the keywords like fork and join. Fork to begin and join to end, right? So you just assume fork means you know how the fork looks like, right? It has a stand like this, and then it has multiple branches. So what it is defining? It is defining the statements here will execute concurrently at the same time period. All of them will execute at same time period. Unlike the sequential block in which they'll execute one by one. Here all of them will execute concurrently. That is the purpose of parallel block. So we'll see the same example with delay and without delay. Since they are executing concurrently, what we have seen, if you have a concurrent execution, there is a chance of race condition, right? That we have already seen while defining two different initial blocks using non-blocking statements like this: A is equals to B, and in other initial block B is equals to A. Since they both are executing concurrently, there is a chance of race condition. We try to swap this, but the swapping is not happening because there is a chance of race condition. We have already discussed this example, how to avoid the race condition by using a temporary variable, right? By using a temporary variable, you can avoid the race condition in case of blocking statements, or you can directly use the non-blocking statements, which will eliminate the race condition, because the non-blocking statements will read first and then write later. We have already seen all these concepts earlier, but here if you see in the parallel block also, we are facing the same issue. Because multiple statements are executing at the same time, there is a chance of race condition, right? So we'll see that with an example. First with without delay, and next one is with delay. We'll see two examples. So similarly, we'll start with initial. Inside the initial, earlier we used begin and end. Now we need to use fork and join. Fork. Uh, let's say if I have my x is equals to 1 tick binary 0, my y is equals to 1 tick binary 1, my z is equals to concatenation of x comma y, and my t is equals to concatenation of y comma x. Right? Since there are no delays, so I opened fork, I have to join to end the fork. See, since this is initial begin and end. Since there are no delays and all of them are executing at time t is equals to 0, there is a chance of race condition here. Race condition. Why? We don't know in which order they will execute. Let's say z is equals to x comma y is executing first. In that case, the x is not at all assigned, so the value of x and y are not defined, right? So the z value will be unknown. So this is what race condition means. Here we don't know the order, so it doesn't give proper outputs. So let's take example with delays. In that case, what happens? Initial begin fork. Okay, I'm defining with some delays. After 5 nanoseconds, my y is equals to this. After 10 nanoseconds, my z is equals to x comma y. After 20 nanoseconds, my t is equals to y comma z, y comma x. Okay. Now see what happens. Initially, all will start at time t is equals to 0 because they are inside the parallel blocks, right? And this y will be executed at 5 nanoseconds. And this z will be executed at not 15 nanoseconds, but it will be executed at 10 nanoseconds. Why? Because all of them will start at t is equal to 0. Unlike sequential block, in sequential block, what happens? It will wait for 5 nanoseconds and then it will perform this statement. But here, this, all the four statements are scheduled at time t is equals to 0. Based on their individual delays, they will execute at that particular time period. Here, the individual delay is 20 nanoseconds, so this t will be executed at 20. In the earlier case, the t is executed at 35 nanoseconds. But here, even though you are using blocking statement, the T statement will be executed at 20 nanoseconds. It is not blocking the earlier statements. Simply, we are using the concurrent assignments using fork and join. So, it will execute at that particular time period, that individual time periods, not the addition of the previous time period. So, that is the advantage of parallel blocks. Okay. So, now let's see what is the nested blocks. So what I meant here is you can use both sequential and parallel blocks together. Like I'll give an example how to use both of them together. So in the same initial block, I'm begin. I'll use some of the statements. Since I'm using begin, some of the statements are sequential. begin x is equals to 1 tick binary 0. Then I can write fork. I am using both begin and fork. Fork, in the fork I can write my y is equals to 1 tick binary 1 and my, let's say, z is equals to x comma y, and then I can end the fork with join, and then again I can write my remaining statement like t is equals to y comma x and end. So these statements will be executed in a sequential order, but these two statements will be executed in concurrent order, right? Up to here it will follow the sequential flow. Once it encountered the keyword for, it will start using concurrent flow. After the join statement, again it will flow with sequential flow. So that is how you can use the nested blocks. You can use both sequential and parallel blocks in the same initial block. So that is all about the behavioral modeling. Now let's see some examples to better understand what are the concepts that we have learned so far. So let's start with an example of thermometric decoder. We call it as a thermometric decoder or one hot decoder. Okay, I'll explain what is one hot. So first of all, we'll see what is a normal decoder. We have already seen a normal decoder, three-stage decoder like this. Right? It has three inputs and eight different outputs. Based on the input combination, one of the output will be 1 and remaining all outputs are zeros. The input combination is 0, 0, 1. Then output O1 will be 1 and remaining all are zeros. Well, if the input combination is all ones, then all these things will be 0 and the last one will be 1. Right? So this is a normal decoder. But what is a thermometric decoder? In case of thermometric decoder, the same 3 to 8 decoder can be represented like this. It has 7 outputs instead of 8 outputs. And based on the input combination, the 7 outputs 1, 2, 3, 4, 5, 6, 7 will be like this. If all the inputs are zeros, then all the outputs will be 0. If input is 0, 0, 1, then output will be corresponds to this. Output will be only one of the output will be 1 and remaining all are 0. This 0, 1, 0, which is a 2 in decimal. So 2 outputs will be 1 and remaining all are 0. Similarly, 0, 1, 1 means 3 outputs will be 1 and remaining all are zeros. Similarly, 1, 0, 0 means 4 outputs will be 1, 1, 0, 1, 5 outputs will be 1, zeros, 1, 1, 0, then 6 outputs will be 1 and 1, 0, then 1, 1, 1. All the 7 outputs are, that is why it requires only 7 different output lines instead of 8 different output lines. You see, we have achieved all the combinations from decimal 0 to 1, 2, 3, 4, 5, 6, 7. Right? All the 8 possible combinations will result into 8 different output combinations. This is called one hot encoding because after every stage, one output is incremented. And this kind of coding is called thermometer coding. See, in thermometer coding, what we'll do based on the number of decimal, that many ones will be present in that output code. The decimal number is 4, then 4 ones will be present in the output code. The decimal number is 7, then 7 ones will be present in the output code. So this is a thermometer or thermometric decoder, and this kind of coding is called thermometer coding. Thermometer coding. We know BCD coding and 8421 coding, all this one. Similarly, we have thermometer coding also. What is the purpose of thermometer coding? Based on the value of the decimal, that many ones will be present in the code. If the decimal value is 5, then 5 ones will be present. If the decimal value is 6, then 6 ones will be present. Now that we have seen what is the thermometric decoder, what is its purpose? Where do we use it? What is the practical application of it? Let's say you want to design a DAC. What is a DAC? It is a digital to analog converter, right? So what is the input of DAC? The input of DAC is digital bits and the output of DAC is analog voltage. So if the inputs is all 0, then my output is, let's say, VDD high. Okay. If my input is 0, 0, 1, then my output is little bit less than VDD. Okay. If my input is 0, 1, 0, then output is 2 times less than VDD. Okay. This is 1x less than, this is 2x less than VDD. Like this, my output transfer function will look like this based on the input. Let's say this is inputs and this is outputs. Then output transfer function will look like this. If the code is 1, then 1x will be decreased. If the code is 3, then 3x will be decreased from VDD. This is a pre-charged circuit. If have charging circuit, it will look like this. Staircase upwards. This is staircase downwards. If 1x, then increment by 1. If 2x, then increment by 2 times from 0. If 3x, then increment by 3 times from 0. We can implement either using like this or like this. But usually we prefer this kind of circuits and we have output is connected to some other input. So how to design that? We'll see. Let's say you want to design a DAC with high linearity. Okay, what I meant by linearity is this is a very practical application, practical example I used in my PhD. This thermometric decoder to get a linear DAC outputs. So what I meant by linear is I'm using the staircase down kind of architecture. So if my input code is 0, then my output should be at VDD. If my input code is 1, it should exactly reduce. Let's say my I'm designing a 3-bit, okay, 3 input decoder. Then let's say my VDD is 8 volt. For easy understanding, I'm taking 8 volt, but usually we'll have VDDs of 1.2 volt and 2 volts, 1.8 volt like this. But for easy understanding, I'm taking 8 volt. At code 0, my output is 8 volt. At code 1, my output should be 7 volt. At code 2, my output should be 6 volt. Like this, 5 volt. It should be as linear as possible. Linear means the amount of decrease should be exactly same for every code increment. Right? From 0 to 1, it should decrease 1 bit or 1 volt. From 1 to 2 also, it should decrement exactly that 1 volt. It should not decrease 1 by 2 or 0.9. If it is like that, then your staircase function should look like this. Somewhere it is decreasing high, sometimes it is decreasing very low, sometimes it is decreasing very high. So this is a very non-linear kind of thing. This is a linear staircase. This is a non-linear staircase, right? If you have non-linear output, then your analog output won't look as you intended, right? Should be as linear as possible. In that case, you will use this thermometric decoder. Why? To generate exactly in normal, if you use a normal R is to 2R, I'm not going into detailed architecture. How to implement a DAC? You can use a R2R ladders, right? R2R ladders. In that case, what happened? You have ladders like this R, 2R, 3R, R2R, 4R, like this, 8R. With this, with different ladders, you will combine. If you want decimal 3, you will combine these two. Then you will get decimal 3. If you want decimal 6, you combine these two. 4 plus 2 will be 6. Like that. Or you can use thermometric encoding in which you will have all or single R's, and then you will use a thermometric decoder here. Let me draw it clear. It will be very, very useful thing when you design practical tags and all. Because if you use the R2R ladder, what happens? Let's say you're using an R2R ladder. R2R, 4R, like this. 8R. I'm taking only 3 bits, so R2R, 4R. Okay. In that case, let's say I want a code of 5. To get a code of 5, I need to combine 4R and R, right? But the 4R might not give you the 4 times of reduction. Maybe it will give 3.9 times of reduction. And once you combine with 4 or with R, the total will be, let's say, 4.8 times or 4.9 times of reduction on the VDD, right? So that is not a linear kind of reduction. So to get linear kind of reduction, what designers will do, they will take all single R's, because single R's will always ensure that there is a 1x of reduction. But 4 kind of R, maybe because of process variation, maybe because of voltage variation, this 4 kind of R might not give you a 4 kind of reduction. It might give you 3.9 times or 4.1 times of reduction. So instead of going with 2R, 4R kind of things, we'll only go with all our single R's. Okay? So we have 1, 2, 3, 4, 5, 6, 7, 8. 8 single R's. By this, what we are ensuring? We are ensuring at least every R is same, right? So in every branch, there will be 1x of reduction. Okay? Earlier, we don't know whether the 4R will give you 4 times of reduction or not because of the process variation. But single R, because everything is the same kind of R, we are 100% sure that these things will give you at least 1x of reduction. If we turn on this R or this R or this R, any R, that will give you 1x of reduction. Now you combine this with thermometric decoder. Then if you want 5, have 8 different outputs that are controlling this. If you want 5 output, then turn on 5 R's. So here you are definitely sure that it will give you 5x of reduction from the VDD. Right? From the VDD, it will definitely reduce 5x because every branch will reduce by 1x. But in the earlier case, if you want to get 5R, you are using 4R plus 1R, you are not sure that it will give you 5R or not. But in this case, you are definitely sure that it will give you 5x reduction. So your linearity of DAC will be improved. So that is where the thermometric decoders will be used to give you the control signals to the resistive ladder. So by using 3-bit input, if you have 0, 1, 0, 2 is your input, then it will give 2 ones and remaining all zeros. These 2 ones will be given to the ladder and 2 stages will be conducting. Similarly, if you have code of 5, 1, 0, 1, then 5 ones will come from the thermometric decoder and it will give as a control signal to your ladder and 5 stages will conduct. So 5x reduction you get. That is how you can design a very linear DAC. Okay, now we have seen the application of thermometric decoder. Now let's design the decoder in Verilog. Now we have seen what is the application and what is the purpose of the thermometric decoder. Now we'll start designing. We'll design using 2 different approaches. In the behavioral modeling only, with 2 different approaches. One approach is by using conditional statement of if else, and the second approach is we can use multi-way branching of case that we have learned, right? We have learned these 2 conditional and multi-way branching. We'll use the same things. One by using if else, one by using case statement. So I'm taking a 3-bit binary input. My input is binary. It is a 3-bit input. And my output is 7-bit thermo. I'm calling it as thermo. So how can I define a thermometric decoder? I'll use if condition. If my binary is equals to 3-tick binary of 000, then my thermo output should be a 7-tick binary of all zeros. Right? I can write 7 zeros or single zero will also be separation. Directly you can write thermo is equals to 0 or I can write 7-bit all 0. Okay? Else, if my binary is equals to 3-tick binary 001, in this case, what should my thermo will look like? Thermo will be 7-tick binary, only one of the output is 1 and remaining all 6 outputs are 0. Similarly, you will write for all the different combinations and at the end you can write else your thermo is equals to 70 binary of 7 ones. By this way, you can write a Verilog code for thermometric decoder using if else statement. The same thing can be written using case statement also. So I'm defining same binary and 7-bit thermo. Here, what is the syntax of case? First write case. What is the expression that you need to check? That is binary and colon. Case binary, no colon. Colon should be there for alternate. Case binary. Now you start writing different alternative. If it is 3-bit binary 000, then what should happen? My thermo should be 7-tick binary all 0. Similarly, if it is 3-tick binary 001, my thermo should be 7-tick binary 000. One will be 1, remaining 6 0. Similarly, you write all the possible combinations up to 6, and you can write the default statement as thermo is equals to 7-tick binary 7. Here thermo will be 7-tick binary 6 ones and 1. Okay, by this way, we can design a decoder using either nested if else if or case. Now let's see another example of a behavioral modeling, which is a 4-bit counter. We have already designed a counter using data flow modeling or gate level modeling using a T flip flops, right? We have designed using T flip flops. Remember, we have designed using 4 different T flip flops for 4-bit counter, and in the same manner, we'll design 4-bit counter using behavioral model. So in earlier case, we need to define either using primitives or assign statement, but here you can directly define the functionality of the counter. What is the functionality of the counter? Counter should just increment its value. So it is like count is equals to count plus 1. This is the functionality of the counter, right? We'll use the same line of code in the behavioral modeling. Like, so let's say my 4-bit counter is a negative edge triggered clock with positive clear. The clear is a positive signal. It is a negative edge triggered clock. So this is the picture of the counter. So in data flow or gate level model, you have to define them individually. But in case of behavioral modeling, you can directly write the functionality like this. Always at the rate of posage of clear, because our clear signal is a positive signal I was giving, or negage of clock. CLOCK. My clock. Negate of clock always at this begin if clear. Clear is equals to 1, then my q is a 4-bit data. I have defined like q is the output of 4-bit data. Then my q is equals to using non-blocking statement 4-tick binary. Else if my clear is not 1, then it will go to else block. Then my q is equals to q plus 1. Simply I am writing the functionality of the counter instead of writing what is t flip flop, what is there inside the t flip flop, or assigning q, d is equals to q, all these things. I'm directly writing the functionality of the counter, and that's it. With this, the 4-bit counter can be implemented using a behavioral model.